So we optimize phi such that q phi of z given x is as close as possible to p theta of z given x. And this approximation helps us to optimize the marginal likelihood. The inference model can be any directed graphical model, for example, q phi of z of x. And by the way, it is parameterized using deep neural networks. So this is just q phi of zm given x. And using the same trick, we assume that we can factorize it. So q phi of zj. By the way, this factorization, although it becomes very fast, the algorithm is very fast, but you lose accuracy. So that's why Markov chain Monte Carlo is much more accurate than these variational approaches, given the parents of zj and x. So these are the parents of zj. So the variational parameters phi, this is a variational parameter, includes the weights. So when I say phi, it means both weights and biases of your neural networks. So the encoder model, now we are ready to talk about this mu. So mu and log of sigma is the encoder neural net of x with parameter phi, and q of phi of z given x is the neural network of z given you have a mean, and the covariance is just the diagonal of z. So the model of the encoder, z is equal to f of phi of x, and then you have some mu here. For example, this is mu I, and this is sigma of I, and your z is here, zi, your latent space, and zi is just mu I plus sigma I epsilon. Epsilon, you sample it, you draw from normal distribution 0 and 1, and here you get your decoder. So your decoder is just the opposite. You get your input by just your latent variables. So this is the architecture of variational autoencoder. First, you learn your mean and covariance, and then you find the hidden variables, because z is just mu plus sigma I epsilon, and then using it you train and learn x. But all of this has only one objective. So let's talk about the elbow, which is the evidence lower bound. Evidence lower bound. So that's the log of p theta of x, which is the expectation of q phi of z given x. Of log of p theta of x. So this is the marginal likelihood. So we want to know what is the log of p theta of x, and we just write it as expectation of q phi z given x of log of, instead of p theta of x, you can write p theta of x and z, p theta of z given x. So it's simple probability. So this becomes expectation of q phi z of x. Now I want to multiply it by 1. So it becomes p theta x and z over q phi of z given x, q phi, again q phi, z given x, and then p theta of z given x. As I said, I'm just multiplying it by 1. And so we can write as elbow plus KL divergence between q phi of z given x, p theta of z given x. So this is positive, and the elbow, the variational lower bound or evidence lower bound, your elbow is the expectation of q phi z given x of log of p theta x and z divided by q phi z given x. So the elbow is a lower bound on the log likelihood of the data. So L theta and phi of x is the expectation of q phi z given x. The log of p theta x and z minus log of q phi z given x. And you can write it as log of p theta minus KL divergence between q phi of z given x and p theta of z given x. This is the KL divergence of the approximate posterior from the true posterior. And this is the gap. We call it the gap because it measures the tightness of the bound. And this is your marginal likelihood. So because this is minus something positive, so we can say that all of them is less than log of p theta of x. So now you understand that maximizing this elbow is just like minimizing the KL divergence. And maximizing elbow with respect to, because we have parameter theta for the decoder and phi for the encoder, is just like maximizing p theta of x. So you have data point, you give it to the inference model qz of x, which is parameterized by phi, and then you sample it, and then you give it to generative model px and z. And all of these things comes to the objective, which is maximizing the elbow of parameters theta and phi, which is the log of p of x and z minus log of q of z given x. So maximizing elbow, it means that you are maximizing p theta of x. And you can do it using stochastic gradient optimization. And your L of theta and phi of your data is the sum of x for the individual points, L, theta, phi, and x. So the individual data point, elbow, and its gradient is in general intractable. However, a good unbiased estimator, this is the unbiased estimator, exists. And we can show you that the gradient of L of theta and phi of x is equal to gradient of theta of expectation of q phi z given x log of p theta of x and z minus log of q phi z given x. So if we are differentiation with respect to theta, and this is phi, so that's why it's easy. So this becomes expectation of q phi of z given x, gradient of theta, log of p theta of x and z minus log of q phi z given x. And approximately, you can say that this is the gradient of theta, log of p theta x and z minus log of q phi z given x. Z are just the samples, random samples from q phi z of x. So this becomes finally the gradient with respect to theta. We can say all of that is just log of p theta x and z, and the Monte Carlo estimator of this can solve the problem. So you notice that this is very easy just because this is very easy because you have theta here and you have the opposite thing, so they are not related. But sometimes the next derivative is really hard because now you are differentiated. This one is hard because phi is the same as here. So we cannot just use simple substitution, p theta of x and z minus log of q phi z given x. So this one is not equal to expectation of q phi z given x of gradient of phi of log of p theta of x and z minus log of q phi z given x. So what should we do? Instead, we use the reparametrization trick. So, and it's just a simple change of variable because you express your random variable z, q phi z given x, as some differentiable invertible transformation of another random variable epsilon, and given phi and so epsilon is just the distribution. You draw it from p. It is independent of x or phi. And so we can say that the expectation of q phi of z given x of f of z is the expectation of p of epsilon. Now everything is easy because it is just dependent on epsilon of f of z, because now we can use a simple Monte Carlo estimator. So you can use gradient of q phi z given x of f of z. It is just the gradient of p of epsilon of f of z. And this is the expectation of p epsilon, gradient of phi of f of z. And so this is the gradient of f of z. The elbow now can be very simplified, can be written as L theta of phi of x. So finally you can write it as log of p theta x and z minus log of q phi z given x. And you use a simple Monte Carlo estimator, theta and phi of x of the individual elbow. So the computation of log of q phi and z. So a common choice is just saying that they are factorized Gaussian encoder. In other words, you after parametrization you can say that. So a simple thing is saying that this is just. By the way, this is the element-wise product, and your model that you should learn, you're learning mu and sigma, which is the. So this tuple is the encoder neural networks of parameter phi of x. And in any transformation, what you care is just the Jacobian of that transformation. For example, here, the Jacobian of transformation from epsilon to z is the diagonal. It's very simple, so it becomes a diagonal of sigma. So the log of q phi of z given x is the log of p of epsilon minus log of the phi of x and epsilon. And this one is the absolute value of determinant of Jacobian matrix, which is, the Jacobian is just epsilon 1, zk, epsilon 1, and the Jacobian. And the determinant of that. So the posterior density is just the log of q phi of z given x is equal to log of p epsilon minus log of d phi x and epsilon. And this is the sum of log of n epsilon I 0 and 1 minus log of sigma I. So you might say that, so how can we use it for natural language processing? And I answered that there are many articles. For example, the 2016 article, Neural Variational Inference for Text Processing by Yishu Miao in Google DeepMind. They applied the variational autoencoder to two things. One is document modeling. The other one is question answering. So this is a set of candidate sentences, and this is the we extract semantic latent variable. So you have a bag of words, and you know what is bag of words. For example, John is 1, likes is number 2 times is used. So any word, you have the frequency and you count the number of times that it has been used. So you give the bag of words. So it's just like text to vector. You give the bag of words to the encoder. Of course, this technique, you can use it in many different scenarios, but here you get the compressed representation, H. And then you give it to a decoder to give you, again, the documents. So it generates some documents. So you give some documents in the form of bag of words, and again, you get your documents. So you give it some, for example, poems, some newsletters, and again, it creates very similar newsletters, very, very similar. Just like what you do with images. You give some images, and it generates very similar images that you cannot distinguish between what is generated and what is reality. And so, and we have the traditional way semantic vector that you have